All right, so let's give it 2 more minutes to wait for more people, then we'll start. Okay, so we have a good number of people here. So first of all, can you guys hear me? Thumbs up. All right, okay. Can you guys see the slides, see my face? Oh, good, all right, good. Okay, so welcome to EE 454, Power System Analysis. And welcome to Fall 2020. So this is, this is probably more weird for me than for you. You have probably taken a lot more Zoom classes than I have. So we'll try to get through this as best as we can. Okay, so I know not everybody is able to attend this lecture live. We have people in different parts of the world. Okay, so if you're watching this recorded, that's fine. So every class will be recorded. Okay, so not office hours will not be recorded. Right? So for privacy issues, will not record office hours. So you can listen to the class. If the TA has 2 office hours, I have 2 office hours. So if you cannot make one of them, right? There's 4 of them. If you cannot make any of them, let us know. We'll try to have more office hours, right, suitable for different time zones. Okay. So other than that, the slides will be posted ahead of time. So right now, there's about 3 slides posted. We'll try to have the slides at least a week or 2 weeks before the class schedule. You can read ahead and you can take a look before you come to the class. Okay, so other than that, I'll start with the little bit introduction about myself, right? So I think I know probably most of you. Most of you have taken classes from me, or at least know who I am. But I've been at UW since 2015. I did my undergrad in Canada. I was graduate at UC Berkeley. So my research is quite aligned with the class. So my research is mostly in power system operations. I do some learning and optimization, and I do a lot of control work. Okay, so most of my career is in academia, but I do have collaborations with Seattle City Light, Peterson Energy, Microsoft, and so on. So as we go through the class, some of the example will be drawn from these folks I collaborate with. Okay. And throughout the class, I'll try to talk about what are we doing now and what are the challenges. Okay. So if you read the book and you read the text, you may get a feeling that we have solved a lot of problems. That's not necessarily the case. And through the class, I'll point out what is the outstanding problems we have in each area. Okay. All right, so contact information is, we have 2 office, I'll have 2 office hours. Tuesday at 3 to 4, Friday at 3:30 to 4:30. Welcome to come to both or one of them. So we'll have a weekly homework. The weekly homework will be due on Wednesday. So the office hours are scheduled to give you a good coverage before the homework due date. So I'll have office hours on Tuesday afternoon. The TA will have office hours. She will have office hours on Wednesday. Okay, so we'll try to give you more than 1 office hour. I will try to answer emails within the day. Right? So there's tends to be a lot of emails for us, but I will try to answer them within a day. Okay, so if you have, so the homework will be due at midnight on Wednesdays. You have a question at 11 p.m. Probably emailing at that time is not the best thing to do. But give me a few hours, I'll try to answer them. So I'm in my office some of the time, as I'm 310. Last quarter, some folks really want to see professors in their office. So if you really want to, you can come. We can shout at each other across the hallway. So if you really want to come to office, come to the building. We can do that. But hopefully the Zoom office hours will cover most of the needs in the class. So interactions is again, let's try to have discussions and try to have some questions. Otherwise, this class will go very quickly. Okay, so we have an hour and 15 minutes in a lecture. If there's no questions, we'll probably finish with an hour and 20 minutes at most, right? So let's try to have questions, try to make this as normal as possible. So there's several ways to interact. One is raising your hand using the Zoom feature. I'll try to notice that. Okay, I'll try to check for raised hands in Zoom. I may not be catch them all, right? So the best way to ask questions is probably just to unmute and say you have a question. Okay, that's probably the best way to ask questions. If you use chat, it's hard for me to monitor chat in real time. Okay, so you have a clarification questions, you have, for other folks in the class, you can use chat, but I may not see it in real time. Okay, so if you have a real-time question for me, I'll just unmute your mic and say you have a question. Okay. So there was some concerns, at least last quarter, about being recorded. So the lecture will be recorded, but after the scheduled time ends, I'll stay online to answer any other question you may have, and that part will not be recorded. Okay, so you have some more personal questions you want to ask, you don't want to be recorded, that's the way you can do it. Okay. So to give this a try, so the TA for this class is Trisha. Trisha, can you unmute and introduce yourself to the class?
Yeah, hi everyone. I'm Trisha. I'm going to be your TA. I've, I think, met a couple of you in the past, but I hope to get to know all of you soon. Yeah.
Right, okay, so yeah, so Trisha will probably be a good contact for you. She will for sure respond to email much quicker than me, right? So, if in doubt, email us both if you have a question about homework, right? So one of us will get back to you. And Trisha will have 2 office hours. The link is in the class website, and the time is out by email. Right? So do ask a lot of questions, and let us help you. Okay. So one thing about technology is Zoom time Toms doesn't work. Happened earlier this September. If that happens, there's nothing we can do. Okay, so if Zoom backend server has a problem, then not much we can do. If you have a poor internet connection, try reconnecting or try calling from a phone, right? So the slides will be up. If you really cannot get internet connection, call the phone number and we'll try to at least follow along that way. And the recording of the class will be up by the end of the day. So, and for the posting the videos, turns out the recommendation from the department is to use YouTube. Turns out that's where the most robust way for students to watch it. And you're not relying on other technologies. So can everybody access YouTube? Are people in other countries who cannot see YouTube? Okay. So if you cannot watch YouTube, please let me know. Right? So that'll be the primary way we'll post the recorded lectures. Okay? We'll just post on YouTube. It's pretty fast. There's bandwidth is handled by them. You can watch on your phone if you want to and all that. Okay. So we use YouTube. If that doesn't work, let me know. But the assumption is that's the way we'll go. Okay. So, right. So the main thing. So the main class website. You should have all gotten this link in the email. We have the slides. We have the links to the recorded lectures. We'll have the homework assignment. Right. And we'll only use Canvas for homework submission and grading. Okay, so the only thing you'll see in Canvas is the homework submission and grading part. Everything else will be done using the main class website. right? So you should download all your homework from there. The homework solution will be posted there. Now, when the exam comes, we'll post the exam there also and all that, right? So that's the main class website. Okay, so you're grading, you submit your homework in Canvas, and Trisha will grade using Canvas there. All right, so any questions about the logistics of the class? About office hours, about recordings, about slides, anything you want to discuss? Are we all good with this setup? Okay. All right, so if you have issues, please let me know. I know there's a lot of uncertainties this quarter. You may have other situations. And the key is to communicate, right? So if you have some technology issues or some other challenges, please let me know ahead of time. And that's make everything easier. Okay, so and having a surprise at the end of the quarter is hard to handle. Right? But if you have issues, do be proactive and let me know. That'll make things a lot more smooth. Okay, and so next, let's look at logistics of the class. Okay, so we'll have one textbook, and this is a so-called required textbook because we'll be drawing heavily from this textbook. Okay, so most of the examples you'll be using this class is found in this textbook. The edition is not terribly important. Okay, so the newest edition is the 6th edition. But if somehow you manage to get an older edition of the textbook, you can use that. Okay, so it's not, but I do assume you have access to this textbook one way or the other. Okay, the edition is not the most important thing, but this is a reference. Okay, for your homework, for your exams, and so on. This is the only required textbook we have for the class. You'll do some programming in the class. Okay? At the end of the day, this class, you can view the sort of the sequence of topic we teach in the class. At the end of the day, is to be able to write a program to solve something called the optimal power flow problem. Okay, so you will be seeing more programming as we go along in the class. And the programming needs is not very heavy. So any language you're familiar with will handle the programming needs, right? If you want to use MATLAB, you can use MATLAB. You want to use Julia, you can use Julia. Or use Python, you can use Python. Whatever other you want to use R, that's okay as well. Okay? But whatever program you want to use, as long as you're comfortable enough in the programming language to handle matrix, right? To know how matrices work, you can multiply and add matrices, you can factor matrices, that sort of thing. That's good enough for this class. There's no required programming language. The only thing we'll use a couple times in this class is something called Power World. Power World, if you haven't seen it, is a standard tool used in industry. It's a pretty old software. So if you download the demo version, you'll see it's not very new. The graphical interface is showing its age. But because it's so standard in the industry, we'll use that for some examples. Okay, so if you're using a PC, there's a free version. You can just download it. It works. If you're using a Mac, there's no version for Mac. So you have to log into the departmental servers and use PowerWorld on those servers. Okay, so you're a Mac user, that's probably something you want to figure out. And we'll be using this for a few homework examples later in the class. As mostly just you have seen the program. Okay, it's so common that you should have seen it at least once in the class. Okay, so we'll use this in class. Any questions about the textbook or programming? Okay, all right. So then the prerequisite of the class is B351 or equivalent. I know a lot of you from that class, right? So if you've taken that class, it's fine. If you are not from UW and you've taken something equivalent, so what we do in E351 is really the first class in power systems. So if you know active power, reactive power, if AC circuit, is something you're familiar with. For example, if you know what a balanced three-phase load in Y connection is, that's fun. That you have enough prerequisite for that class, for this class. Okay? So we don't assume a lot, but we do assume enough knowledge coming from E351. Also, the something in this class is basic linear algebra. Because at the end of the day, we'll be talking about pretty large systems. Okay, right? So think of a power system. There are easily tens of thousands of components in the system. Of course, the example we do will not be that large. But once you have many components, it's much easier to talk about in matrix algebra notation, right? To saving writing out everything. So again, towards the later part of the class, everything we do will be in matrix vector notation. So this is something you should be familiar with, right? So be familiar with, multiplying matrices, knowing what eigenvalues mean and this kind of thing. Okay? So these are the prerequisites for this class. Oops. So the grading, will be this class as 3 parts. Will be homework and 2 exams. Okay? So homework is 50% of the class grade. It's assigned weekly. Okay? So this week's homework is out already on the class website. It's mostly for review, and it's due the Wednesday after. Okay, so you submit this using Canvas. Pretty standard process for homeworks. Okay, and the thing is, so if you cannot submit the homework on time for any reason, it's better to let me know beforehand. Okay, so we'll be flexible with the submission policy. Right, so in previous years, there's no late submission whatsoever. But for this time, if you have to be late by a few hours, we'll we'll allow that. But do let me know ahead of time. Again, that makes things a lot easier. We cannot submit homework exactly on time. So exam, we have a midterm, that's 20%. We'll have a final, that's 30%. Of course, I'll be remote. So remote means, open everything. Okay, whatever you want to use, you can use. Okay, slides, textbook, computer programs. You can Google stuff if you want. Okay, whatever technology you have access to, you're welcome to use it. The only thing I ask you to do is don't communicate with each other. Right? There's really no way I can really enforce this. So this is more of honor code. Okay, so do not communicate with each other, and we'll try to be diligent on comparing solutions. So sometimes if you copy or you communicate, it's obvious that you have communicated, and we'll try to be diligent in that case. But the other settings, just don't, just try not to do that, and you can use everything else. Okay, in some sense, this is more closer to real life. So in real life, really, nobody says nothing engineering closed book in real life. Okay, you're Googling all the time. I certainly Google all the time, right, when I'm doing something. So this is a proxy of that. Okay, so but don't have a false sense of security, thinking that it's easy because you can Google or you can use computer. Right, still a 2-hour exam. Right, you still have to do all the questions on time. Okay, so that's the thing about the exams. So any questions, suggestions about the homework or the exam? Anything about the grading policy? All right, so again, we'll try to be flexible with the grading policy, but who knows at the end of the class, what we have to do. But this is the sort of the preliminary grade breakdown for now. Okay, so 50% homework, 20% midterm, 30% final. We'll adjust if necessary. Right? We'll adjust toward the end if necessary. If you have some concerns, again, let me know either by email or come to the office hour. Right, so as I said, the first homework is out. It's a review of the AC circuits. So the first homework you should be able to do without doing anything in this class. Okay, so this is really a check of the prerequisite. Okay? We're really checking prerequisite using the first homework. So you haven't done, if it's been a couple of years since you took 351, to have a look at the homework. It's not very difficult, but may appear long. So this will be longer than the standard weekly homework. This just, we want to check you have, remember all the equations, basically. That's 351 covered. Okay. So it's out, it's due next Wednesday at 1 minute before midnight. Okay, so submit to Canvas, and we'll have the solutions posted after that. Okay. So this homework. All right, so now let's get started with the objective of the course. Okay, so really the objective of the course is the following. Basically, we want to know is, I have different ways of generating electricity, generating electric power. How do I get this power to the end consumers? Okay, so we'll not worry so much about how do we generate power, or about what we do with the power we get. Okay, this class is mostly about this arrow in the middle. This is the focus of the class. Okay, so our focus will be, how do I transfer power from the power plant to the end users? How do I do this reliably? How do I do this efficiently? Okay, so in 351, a big part of that class is generation technology and motors and stuff. In this class, not so much. Okay, we'll assume the power is generated somehow, and our goal is to ship it to the end consumers, and they can use it however they want to use it. Okay, this is our goal. And this is actually a big industry, right? So if you look at the estimate, the best estimate is this is about just under $1 trillion. And this is simply the transmission and distribution part of the grid. Okay, so this accounts for a big chunk of money that's actually being transferred every day. So imagine you're paying electricity bills, our university is paying it, your dorm is paying it, anybody who has a light in the UC electricity is paying it. Each of your bill may be small, but they all add up. There's actually a huge economy behind this transfer of power. Okay? And our goal is trying to understand how this is done. Okay? How this is done. So often when we do a example, we'll say, okay, we're 5% more efficient, which seems to be a small number, but 5% of $1 trillion is not small. Okay, so if you're working in the industry, if you can improve the efficiency, let's say by 5%, you win a big award in the industry. Okay, just because the base number is so large for the amount of power and equivalently money that's being moved around every day. Okay. So, and if you look at power system engineering, it's a little bit strange. So 10 years ago, you read a newspaper, you never see almost anything in the news about power. However, if you look at the newspaper nowadays, just look at New York Times, right? And say, there's a basic section devoted to what happens to California power grid. Okay, so we probably all heard of it. California has been having rolling blackout in the last 2 years. Okay, and our job, whenever you see a headline like this in the newspaper, that means we have not done a very good job. Right? Our goal is to avoid the newspaper having this kind of headlines. Okay, and this is actually a worrying trend for the people in the industry. Okay, this is a pretty worrying trend. Okay, so if you think about, does anybody know what is the standard quality of service in the industry? Meaning, on average, let's say, so on average, how long do we expect to go without losing 1 hour of power? Right. So this is the industrial standard we use. Okay. So we'll eventually all lose power sometimes, but really we care is between, let's say, losing 1 hour of power, what is the expected time? Anybody have an idea? So let's try this interaction in Zoom. Anybody has an idea how long this is? Is this a year, 6 months? What is the standard? that we get judged on. Anybody have a guess? Is every 5 years?
I would guess every 5 years.
Right. So no, it's actually more. The calling service is higher than that. So the calling service we try to get to is every 10 years. So the expected loss of power is in every 10 years, each customer will lose 1 hour of power. And this is actually the standard. So if you don't meet this, you actually get a penalty from the government. Okay, so NERC, which is the North American Electrical Reliability Council, comes and penalizes the utility if you lose power more than 1 hour for every 10 years on average. Nobody on the West Coast is meeting this right now. Okay, so we're very far from meeting this number. And the trend is very worrying. Okay, 20 years ago, we're not bad. Nowadays, if you live in California, you can expect to lose power for about a day every year. We're in the Bay Area. Okay, and this is because one, there's more demand, right? Summers are getting hotter, and there's more demand. And we have not planned super well for this, although it's not as simple as what the news article is making out to be. Right? It's a hard problem, but looking back at it, we could have done a better job at it. And also the second is because of all the fires. So whenever we have big fires, what happens is if a transmission line happens to be on top of it, right? If it's close to a transmission line, we have to de-energize the transmission line. Basically, we have to take the line out of the system. And that creates situations that we never thought of. There's many lines which we build, and we never thought the line would have an outage. Okay, we build them very robustly. We spend a lot of time maintaining the lines. People know, these lines are built 20, 30 years ago. We never thought there would be a forest fire, or be Wi-Fi under the line. We didn't anticipate it. Then suddenly we can't ship enough power to the demand. Okay, so all this is happening right now. And you will see part of this class is how do we try to deal with this? How do we try to deal with the fact that we may lose lines in the power system? And then why it's becoming harder and harder to do in practice. So it's not that the folks in California, they don't know this, right? There's sophisticated software trying to do this kind of things. But you still have to have rolling blackout, which is probably the worst sign for a power engineer if we get into rolling blackouts. Okay, and then in this class, we'll try to see what tools we try to use to avoid this, and then why we're not always successful. And for you, if you go to industry and you work on this, what kind of problem you'll be dealing with. And the good news, is that suddenly the field is a lot more exciting. Okay, if you work in the utility, let's say 20 years ago, your job is, is of course meaningful. Is that all that exciting? Debatable. Now this is very exciting. You will be developing new tools. You will be developing new practices. You will be doing new things that has not been done before. Because the system we have is changing so much. Okay, so it's quite exciting from a research perspective. And the societal need is to, let's say in 5 years, let's not have any of this headline. Right? In 10 years, let's not have headline that keeps saying power outages. Okay, and so the goal is try to avoid this. We'll try to integrate as much as renewable as we can. Okay, that's the sort of grand challenge we have. And if you work in the industry, this will be part of this. Okay, so it's quite exciting time from that perspective. A lot more stressful. You talk to people in Puget Sound Energy, they're stressed a lot more, but at the same time, they're saying their life is much more exciting. Okay, so that's the trade-off right now. So why is reliability a hard problem, right? So why is planning for a large system so hard? Why does California have to have rolling blackouts? And if looking at the current situation for Washington State, as a reason is a 50-50 bet whether we'll have rolling blackout in 2 or 3 or 4 years as well. Okay, just looking at the current trend. Okay, so more disruptions may be coming. And that's because reliability is really, really hard. right? Power systems are large systems. There's a lot of lines, a lot of transformers, a lot of loads, a lot of generators, and they can all fail. Okay? So each one of them may have a very low chance of failure, but when you put 100,000 of them all together, now then with reasonable probability, one of them will go. So that's one thing we have to be mindful of. And the failures are common, getting more common. Okay? So the weather is more extreme. For example, you guys may remember the snowstorm we had about, 2 years ago, no, 2-3 years ago. That snowstorm was a huge surprise to the utilities around the Puget Sound area. That was not something we anticipated would happen. The grid was not designed to withstand a week of snow, basically, but we're having that now. Okay, so, and we're trying to have new ways to try to, make the system more resilient. And another thing that's bad in some cases for the system is we have an aging system. If you go out and look at the power lines, especially the high voltage lines you sometimes you see driving on the highway, those lines are most likely more than 30, 40 years old. Okay, we're not building more lines. So we have to deal with a system that was designed, half a century ago, that has facing all these new challenges. Okay, so that's difficult, something very challenging to do. And the system is quite complicated, okay, because it's so big, and because the physics is not easy to deal with, because the power flow equations are basically nonlinear. The system is complicated, and we don't really have a very good understanding of when this should work and when it should not. So what we have is we have a lot of unpredictable failures, meaning that nowadays when you see a failure, it's actually a surprise. Okay, it's a surprise that something we haven't thought before. Okay, so if a line fails, every year, we know how to deal with it. But nowadays, a lot of failures, just we never anticipated, and it's hard for operators to very quickly deal with. And the goal for operators is actually, so if all you want is reliability, if you don't care about the cost, then there's ways to make the system extremely reliable. Okay, so if you give us, $100 trillion, I can build you a grid that will never fail. That's not the reality we're in. Okay? So our life is we have to balance two things. One end, we want to make the grid reliable, right, towards unforeseen events. Other side, we have to make it economical. Okay, so reliability is all good and well. If all your electric bills went up by tenfold, none of you will be happy. Okay, so there's an intrinsic balance between how reliable I can make the grid and how efficient it is. How much, how do I minimize the cost? Okay. So, and balancing this is kind of challenging. Because what we're balancing against something that has a very small chance of happening, okay, right? Let's say, power outage. Power outage may cost us $1 million, but the chance of that happening may be very small. So how do I think about this problem? How do I think about this kind of issues? You get into the sort of classical insurance problems. When you're designing a system, how do you think about a cost that you will always have? That means generating power, transmitting power, versus a cost that you may have happen, but the chance of happening is very low. Okay, and this kind of calculation is challenging to do. It's not the easiest thing to do this calculation. So, okay, and this also has numbers that's very hard to quantify, right? Do we know the probability of outage? Not really. Okay, we certainly do not have enough outages to have a good estimate of probability. Do we know the cost of the outages? Again, not really. Okay, as there's a cost of outage $1 million. It's hard to say. If my house loses, power for 1 hour, it's probably not a huge deal, right? And but if, let's say, a hospital loses power for 1 hour, that's obviously a much bigger issue. So these are things that system engineer has to think about. And it turns out engineers are not very comfortable with probability. Okay, so if you look at the the standard approach today is to say, let's not talk about probability. Okay, we don't know how to interpret it. We have a lot of issue trying to communicate this to the customers. If you tell the customer you have a chance of losing power, have 1 in 1,000 chance of losing power, the customers don't know how to interpret that. Right? The engineers were not very comfortable dealing with that. So really the approach is talk about things in deterministic cases. Okay, meaning that reliability, what we talk about is, so what this tends to come in as the following. Let's not talk about probability. So we'll make the following assumption. This is, if any one component fails, the power should be on. Okay, this is how one thing you can convert a probabilistic question into a deterministic question, meaning that we'll guarantee the power stays on for any one component failure. What happens if 2 components fails? We'll assume that never happens. Okay, this is a lot of current thinking for the existing community. Okay, so that's how we think. Okay, and this, and this basically says achieving 100% reliability is impossible. So our reliability criteria will cover, the reasonable event. 1 component fails. 2 component fails is a very small probability. I make no guarantees whatsoever. Okay. So obviously, this is not right now a correct way of thinking about the problem right now. Okay. So can you guys see some issues with thinking of the problem this way? Taking this sort of very deterministic approach. If 1 thing fails, I guarantee it works. 2 things fail, never happen. We don't care. Any challenges with this? That in your mind, is that how failures happen in power systems? Do we have one-line failures?
Failures are correlated with each other. You may have a common cause that causes multiple things to fail.
Right, exactly, right? So failures are not independent. If I have a windstorm, if my line fails, the next line to me will also likely to fail. Right? This kind of N-1 deterministic interpretation misses a lot of failure that happen in practice. Okay? If a fire comes along, I have 2 transmission lines going, fairly close to each other. Both are gone. Okay, so the failures are no longer independent, and the failure mode is actually quite complicated. So just to ignore them doesn't work anymore, and we see this in practice. You see more power outages. Okay, you live in the Puget Sound area for 4 years, you will probably experience a power outage. I have seen quite a few, right? And all of them say, oh, I make sure it's N-1 secure. If 1 thing fails, it still works, right? But it's very rare, or it's rare to see only 1 thing fail. Normally, many things tend to happen together, and that the current research, there's a lot of research trying to understand, computationally wise, how do I compute things in a more probabilistic way, and how do you think about this policy wise? How do you communicate? How do you communicate to folks that about a probabilistic standard rather than a deterministic standard? And the analogy sometimes we draw is closer to the internet. Okay, so your internet provider does not give you a deterministic guarantee. Okay, you could have internet outage. That happens. What happens? How does your internet provider work? Right? Your internet service provider says, I'll do a best effort service to you. And most of the time it works. And there's some push for a power industry to go like this. It's going from a guarantee service level, which is becoming almost impossible to do now, to a best effort service, which may actually be better from a customer's point of view. So again, this is something we'll look at later in the class. Okay? So just to have a more concrete example, let's say we're looking at reliability issues, and the question is, what can go wrong in this system? Well, many things can go wrong in this system, right? I can have a generator failure. Yeah, my generator can fail. My line can fail. And if any one of these components fails, then my system doesn't work. Okay? So this is a system that's not very reliable, right, in any sense. It's subject to single component failures. So N-1 criterion says, we should be able to withstand any single component failures. In this case, the way to withstand this is to say, instead of one generator, I have two generators. Instead of one transmission line, let's have two transmission lines. Okay? In this way, let's say if this thing fails, it still works. Okay? If one of the transmission line fails, this thing still works. Okay, so this is what N-1 criteria means. And the assumption is, the chance of both line failing or the chance of both generator failing is quite low. Okay, it's quite low. Right? So this is what we have in N-1. Right? So then there's a trade-off with this kind of N-1 way of looking at things. Because we can do a easy thought experiment. Let's say that each line are similar. They can have a capacity of 200 megawatts. 200 megawatts. Okay. Then and assume that this generator is always on. Okay, so the generator doesn't fail, but the line may fail. Then what is the maximum power A can deliver to B if I insist on N-1 standard, N-1 contingency? And how much power can A deliver to B?
200 megawatts.
200 megawatt, right? So that's the most I can do. So this is 200 megawatt, right? Because I need to account for what possibility of line failure. This is obviously not very efficient. Okay, I built a transmission line. I built two transmission lines. Somehow I have to always leave one not carry any power because I'm afraid of something happening. Okay, so here you can immediately see the trade-off between reliability, which is I should withstand failures, and efficiency. Okay, I spend $50 million building a line, I don't get to use it. Okay, so and for example, if generator A can generate a lot of power, somehow I'm limited by this reliability standard, right? So I cannot very efficiently operate the system. Okay? And this is what happens in a simple system. If you look at a bigger system, okay, so if you look at resource allocation, right? So if you look at resource allocation, basically this problem gets much, much harder if the system is larger. And it's not so obvious anymore. What is actually the most economic way to generate power? So for a two bus, two transmission line system is quite easy. We know it by inspection. At the end of this class, you can think of the whole class building too. If I give you a much larger system, how do I make sure I most economically generate power subject to the N-1 criteria? This is actually an extremely hard, difficult problem. So we'll look at simplified models, but that'll give us a good idea of what we do in practice and what are the challenges and what are the tools we can use to address the issues. Okay? So that's what we'll do. And the problem is hard, basically boils down to the system is super large. Okay? So we probably have all seen this again diagram. This is a North American system. Okay? So North American power system. So the Canadian system and the American system is actually fairly well integrated. So electrically, it's one big system. And the regulatory body actually a lot of times covers both countries. Okay? And so we have the Western Interconnect. This is called WAC. We have the Eastern Interconnect. And this is actually pretty divided in the middle. So this is mostly a clean divide in the middle. There's a very few lines connecting to interconnects. And so they're essentially two separate systems between them. And then we have the Texas system, ERCOT. This is called the Electricity Reliability Council of Texas. And Texas manages its own system. The Texas system is not connected to anything else. So this is very clean divide in Texas. Okay, it's an entirely own system. And this turns out to be a good thing, at least research-wise, because it turns out ERCOT is the most sort of innovative system we have, because it's really a system that anything goes. Whatever new things you have, you want to try, ERCOT will tend to try it. Okay, so being Texas, they don't like regulations, they don't like all those kind of things, and you can try whatever you want. So it's actually a very nice system for research. To read papers, about 50% of the papers saying for ERCOT this thing happens, because this is actually the system we try things on. For example, wind. ERCOT by far has the most wind. Demand response, ERCOT by far has the most demand response. Okay, so ERCOT somehow, in this case, actually makes research very friendly to research. And we all try things on this system. So something happens, right? You have European Union. European Union is essentially one large system. Okay? One large system. And so if you look at Brexit, right? So Great Britain tries to exit EU. If you look at the agreement, about 50 pages is what to do with the electricity grid. Because this is connected, they're the same grid. Okay, so all this is the interesting thing when you operate grid is it forces us to have a standard market in how to operate the grid. And that turns out to be a very interesting engineering problem, actually. Okay. So let's think about the question is, why do we want large grids? Any suggestions, right? So even for ERCOT system, it's quite large. So even Texas, is not a small system. If you look at Eastern Interconnect, it's a huge power system, right? Serving, about 200 million or so households, 200 million people in the Eastern Interconnect. So, and this is by design. We sort of build a system on purpose to be this large and this geographic spread out. So what's the reason to do this? Why do we adopt this system? Why do we connect, everything we can connect?
Can you allocate resources across larger areas?
Right, so one is efficiency, right? I want to allocate resources. A lot of times power is generated not where the people are. Okay, so if you look at, for example, wind generation, there's a lot of wind here. Okay, so I need to get the wind to somewhere when the loads are. I need a grid. And it turns out to be very economical, connect system this way. Okay, and this is actually more reliable because if I lose, let's say, a generator anywhere in this system, let's say, I lose a small part of the system here, it's okay. I have a lot of backup resources from this. Yeah, so yeah, redundancy, energy trading, energy resilience, so these are the right ideas. But then, is there any drawback if my system is super large? Right, so right now they're actually trying to move away from super large systems. For example, if you look at no, not necessarily the cost of transmission, not necessarily. So if you look at, so in the chat, somebody said, transmission, that's not actually, it's not a cost issue mostly. So if you look at, for example, Google, Amazon, all those people, they're actually advocating for much smaller system, much less connected system. Any reasons why that's the case?
Well, I guess if you're running like a server farm or something, you need energy all the time. So is it like a redundancy thing?
Right. So the larger system is actually the trade-off is quite interesting. It's more resilient on one end, it's also less resilient. Because if everything's connected, things tend to go together. A lot of times when you bring down a couple of generators, the entire system may get wiped out. Okay? That's for the good example is the 2003 blackout. It's basically caused by one transmission line having outage. And that brought down the entire, almost all of the Eastern internet. Okay? So when we have a large thing, we have some things that have cascading failures. Okay? Right? So we have a interesting balance. On one hand, large system is more resilient. On the other hand, is less reliable. Okay? So that's an interesting trade-off. And this is actually not all that well understood. If you look at the engineering policy pushes, there is a distinct two direction people are advocating for. One group is advocating for even larger system. Basically, you connect the three North American systems all together. There is a lot of people advocating for microgrids. Microgrids meaning city scale or even smaller. Okay, both are being talked about. And a lot of attention being paid to both. Okay, and this is an argument we're having. And the engineering one is sort of technically it's hard to understand which one is better or worse than the other. Okay, so there's a lot of trade-off between size, reliability. That's not well understood. And the interesting thing is, so I was in a meeting where Microsoft and Amazon were advocating that they want microgrid. They're happy to pay money, basically to say allow my server farm, I'll build a microgrid, right? And for the people who live along that town, I'm happy to pay them energy for free. And the one question that brought up, this is not exactly equitable, right? We don't want a situation where people who has money go build their super resilient microgrid, and people who, the less advantaged communities are left with not reliable power. Okay, so there's a lot of resource allocation that comes into this. And there's many factors associated with this that not terribly well understood. But it's an interesting research question that we're looking at. Okay, so that's something you can think of if you're working in a utility. If you're working in a utility or for a system operator, these are the questions you'll be faced with. Okay? And there's not necessarily a right or wrong answer, but it's good to be mindful of all these issues that may come up with this. Okay? And in the chat, somebody said, so Milo said latency. Latency in power system is generally not a issue. Okay, so it's not a communication. Right, this isn't signal. Okay, so right, so different times for signals in power. So this is a good. This is a good thing to know how fast things propagate within the network. Okay, so let's have a thought experiment. Right, let's say I have a power outage. So let's say in a nuclear power plant. Okay, nuclear power plant has a fault, goes offline. Then this fault will propagate to the rest of the system, right? Will eventually get to every part of the network. How fast do you think this propagates through the network? So this is some wave. This is basically a disturbance in the electromechanical wave that goes through across the network. Anybody have a guess of the rough speed of the wave that flows here? So it's not speed of the light, right? So it's not that fast, but it's not terribly slow. Any guess, roughly, ballpark? 100 miles per second, 1,000 miles, 10,000 miles per second? This kind of wave traveling. So 1/3 of speed of light is also very fast. So this wave travels about 500 miles per second, right? So the distance of the continental United States, about 1 second. That's how far the things travel. So this also gives you an idea of how fast you have to communicate, right? Things. If you want to react for a big disturbance, this is sort of the time scale you have for reaction. So these are the ballpark numbers disturbance. So If something happens in California, we'll feel it about half a second or 1 second later. These are how fast things travel. Okay, so large connection does bring challenges, and the part of this class is how do we at least try to attempt address very large systems. Another part of the class which we'll try to get to, or at least have a good idea is renewables. Okay? And the renewables, mostly we mean, in this class, we'll say renewables, we'll take it as a shorthand for wind and solar. It doesn't mean hydro is not renewable, right? Geothermal is not renewable. Basically, we use renewable as a shorthand for something that has a variable output, or something that has a very limited controllability. Right? So hydro is definitely renewable. Just we can control it fairly easily. Okay, so we put into the traditional generation category. Renewable means wind and solar, and these actually introduces a lot of uncertainties into the system. And the system we build is not with uncertainty in mind. Right? We never build a system thinking that we have this much uncertainty. So operational wise, it's interesting to think about how do I operate a system that has renewables, has uncertainties, and the infrastructure wise will not change all that much. Okay? So renewables is not where, often renewables is not where people are. We have to get the power to places. We're very limited in our ability to build new infrastructure. And this is actually exciting topics for operational engineering. Because the best we can do is through algorithms and computation, right? Not by building massive new infrastructure. If we can do that, that's an easy solution, but we cannot. Then a lot of interesting things coming up with operations. How do you dispatch these renewables and try to maintain reliability and keeping the cost down and the efficiency at the same time? Okay? So let's take a 5-minute break, right? Give everybody a chance to take a break. So if any questions, you can ask. I can answer the questions. Don't have questions, take a break. We'll come back in 10:33. Okay, take a 5-minute break. All right, okay, so let's continue. So basically this class is about power system engineering. And the thing we've covered is mostly power system operations. Okay, so power system operations, as we are gonna assume that all the generators, all the transmission lines, all the transformers are where they are. Okay, so the infrastructure are already decided for us. And our goal is how to make the best use of them, and how to find the least cost solution of using the system. Power system planning and design is a little bit different. Power system planning is to decide where to build new lines and generators, right? So within we work for a system operator, work for utility, that'll be sort of two different departments within the utility or the system operator. One will be operations, one will be planning. Okay. Power system turns out to be power engineer is a very computational subject. Okay, so if you work for a power system company or you work for system operators, most of your time will be actually spent on coding and running computational experiments. Okay? And the reason is we cannot do real experiments. Okay? In power system, it's never to say, oh, let's build something. If it doesn't work, let's do it again. Okay, that's just not the way things are done. Okay, we need to be, right? If we decide to build something, it is that way. Even if things happen, we're not going to change infrastructure. We're not going to move a power line. Okay, we're not moving a substation. It is where it is. And the goal is to design around it. So obviously, a lot of computation has to go around it. Okay? When you simulate a lot of stuff, okay, you'll be sitting, you'll be basically coding and simulating things and try to make sense out of it. This class, one will teach you how to write code. How do you formulate these problems? How do you simulate them? And another thing will be try to gain some intuition. Right? We'll try to gain some intuition. Because we cannot exhaustively simulate everything, especially once renewable comes online. We cannot, there's no way we'll simulate even 5% of our possibilities. Okay? So we need to have good intuition of what to study and what to simulate. Okay? This is something we need. And this class will try to build some intuitions here. We'll try to understand what is easy, what is hard, which part of the system likely to have problems. Right? So the class goes hand in hand. How do you formulate problems? How do you solve them using computational tools? And how do you simulate? Right? How do you develop some intuition? How do you look at a system to know, where are things likely to go wrong? So these are the big things we try to get out of the class. So the tools we'll be using are, sometimes called simulation tools. And this is for power flow. And you see this in Power World. Right? So simulation tool says, I have a system. Let me change the load a bit and see what happens to the generation, what happens to the voltage. I have a system, let's say this line has a fault. Dynamically, let's see what happens to the system. Is it still stable or not? Okay, this is sometimes called simulation tools. And then we have optimization tools. The optimization tools means that, how do I optimize the generators? Given a choice of this generator generating 100 megawatts versus 80 megawatts, how do I choose, right? How do I optimize the system? And then we can, of course, combine things together and think about optimizing while taking reliability into account. Okay, so these are a big combination of tools. And if you look at commercial tools, the very expensive tools tends to be solving this kind of problems. How do you optimize while subject to a security constraint or reliability constraint? Okay, these are, you work for GE, for example, most of your time will spend on developing this kind of tools for various customers that you have. And for this class, most of the time, we'll be looking at something called the steady state simulation. Okay, meaning we'll take a snapshot of the system. Okay, we'll take a snapshot of the system. Assume this is the state of the system. I'll try to optimize this system. Okay, this is called a steady state simulation. So meaning that we will not be dealing with differential equations for most of the class. Most of the class are algebraic equations. This is the voltage, compute the power. Okay. Later so if you take more classes, they will cover more dynamic simulation, dynamic behavioral system. Okay, so if let's say a line has an outage, the system will not go to the new steady state immediately. There's some transition. How do you understand this kind of transition? That's a little bit more advanced in this class. This class is mostly about the steady state. We'll assume that even a line has an outage, we'll immediately go to the new steady state. And we'll understand what that steady state means. Okay, we'll not worry too much about dynamics. So if you look at the course outline, we'll look at modeling, bunch of modeling things. Right, we're looking at modeling of transformers per unit system. We'll look a little bit at modeling generators, just so we have a consistent circuit theory. We'll look at modeling transmission lines. Then we'll try to basically, so all of this you can look at as getting a power system into a circuit. Okay, so outside the real system has big transformers, big transmission lines. A transmission line that's 1,000 miles long. Our goal is to represent that as a single block in the system. Okay, so the goal of the first part of the class is, let's say I have a transmission line, that's a tower that's 100 miles long. How do I convert this to a circuit? Right? Why does this work? What assumption are we making? How do I make this conversion? That's for the sort of big part of this class. The first part of this class is we're look at all the complicated components we have and boil them down to a single discrete component circuits. That's our goal in the first part of the class. In the middle part of the class, you can view this as a middle part of the class. This is really given a circuit, solving the circuit. Okay, so we'll convert the actual system to a circuit that has basic RLC, has RLC circuit. How do we optimize power flow in the circuit? Right, so this is solving the circuit. So that's for second and the major part of this class. Then the last part, these two, is a little bit more on the dynamics, but we're not going very deep. We're not going very deep. This was last week of class. Now this does the following. Okay? So if you look at the time evolution, basically think of this time. Okay? Think of this time. And we're solving basically this kind of operation problems every snapshot in time. So this may be hour 0, hour 1, hour t, so on, right? For each snapshot and an hour, we'll solve the optimization problem. We'll make sure supply equals demand and so on. What happens in the hour? Right? Somebody comes and flips a light switch. I turn on a computer. Right? So in this hour, the system must still be balanced, right? Things still happen. So then the last part of the class looks at what happens within the sort of 1 hour time interval. And how do I maintain system balance? And so this is the organization of the class. All right. So any questions about the class outline, course outline? Any suggestions? Anything you're not happy with? All right, okay. So if during some time in the class you want to see something more, something less, let me know. Okay, and do let me know early, right? Because I'm trying to have the slides, a week or so beforehand. So it'll be helpful for me to know the subject you want to cover a little bit early. Okay? Right? And the midterm will be in class, and the midterm will be, somewhere here. All right, so we'll have a midterm. depending on how exactly the course flows. Will be in the middle of the course. Okay, it will be a, basically in the normal class hour, you'll do the midterm. Right? So, all right, so here I guess is a good point to ask. Any suggestions you have for teaching class over Zoom? So internally, the faculty, the ECE faculty, we had a big meeting last week, and we looked at a lot of the feedback you guys gave basically from last quarter, and the consensus is you are all not very happy about the job we did. Okay, that was the overwhelming consensus in the feedback we saw. And so, right? So if you have any suggestions, now is a good time to say, what happened in the last quarter that you found very useful, that you want me to adopt? What you found in the last quarter that was very bad, that we should avoid? Any suggestions you have? Now, do you want? Okay, so one question in chat is, what kind of opportunity are there for collaboration in this class? Do we have group projects? There's no group projects because we have enough people overseas and not in the same time zone. That will make presentations and things very complicated at the end of the day. But the good thing is you should collaborate on the homeworks, right? So the homework, other than this week is a review homework. But homework going in the future, there'll be one question at the end of homework that's a little bit challenging. Okay, so that requires some thought. May not be very standard, maybe a what if question, right? I mean, open-ended question. That question you're encouraged to collaborate on, right? Think together, you can try to work out that question. So example of that is, for example, so we can take a standard transformer, okay? And so next week and later this class will look at transformers. We'll have a lot of questions about transformers and so on. And the homework mostly will be standard transformer questions. But you may see one question that says the following. You have a system, we have 5 transformers, and we have a solar storm, and it blows out one of the transformers. Now you have 4 transformers, but I still need 5 connections in the system. How do I do this? Okay, you see this kind of questions. Or the problem may say, instead of a normal transformer, I want an auto transformer. Do the calculations with the auto transformer and tell me why it's better or why it's worse. Okay, this kind of thing. Or the question may say, Seattle City Light spent about $200 million building the South Lake Union transformer substation. Why did it take $200 million? Okay, what in there is actually $200 million? Okay, what kind of equipment is that expensive? Okay, so you see this kind of open-ended question in the homework of similar flavor. And of course, you can collaborate other questions, right? But this kind of question, you're encouraged to collaborate. Okay, so you can, talk among each other in the class. Right, so how will the exams be different this quarter than in person? So in person will not be open computer for sure, right? So the exam in this quarter will be just open things. You can Google things. You can search in your book, right? Have a PDF version of a book you can search. You can, you don't have to print out all your notes and bring to class for exams and so on. I will be online to answer questions, right? So that'll be similar. Zoom will have a Zoom thing that's open. It'll be, similar to this setting. You have a question, unmute yourself, ask me. Okay. There's somewhere indicate roughly where we'll follow around record book. Okay, yeah, so that's a good suggestion. I will indicate that. After this class, I'll go to the website and indicate where we are. The chapters were roughly along the textbook. Yes, I'll try to indicate that. Yes. So going back to the exams, that'll be different. Let's open everything. I'll try to answer questions. Technology-wise, there are some issues with the exams, right? So how do you turn it in and so on? We'll work that out. If you need more time to do the exams, for example, if you're living in your home, you're very distracted, you have other people to take care of, you don't have a quiet environment. These things we can do. There are standard policies the university now has worked out. for this kind of exams. If you let me know, we can make special considerations. For example, if you need more than the normal 2 hours for the exam, right? Then let me know, and the university has a way to deal with that. If you need a space on campus to take the exam, right? For example, you have roommates, and you guys both have exam. Your roommate will have a class presentation at the time you are doing your exam. That may be very distracting. All these things we're aware of. If you let me know, at least a month early, or as soon as you figure it out, there are dedicated spaces that university has worked out for you to take this kind of exams. Okay, so you're not on your own there. Right? Just communicate with me. Right? There are ways we can do it. There's ways. So since we have people overseas, we'll have a off-cycle exam, so-called. There'll be, because the exam for them is 2 a.m., we'll have another exam for them that's not. That's not that's more convenient, right? So you don't have to wake up 2 a.m. taking exam. Right? So we'll have this kind of exam. But again, the key is let me know the time zone you're in. Right? So right now, the only time zone I'm aware of are people in Asia. Okay, so we'll have an exam at night. If you're in Europe, then also something let me know, right? Then we need, other time zones to worry about. All these things can be done. I think just communicating with us, so we have enough time to plan for this. That's important, right? So knowing, a day earlier than the exam, saying you suddenly think I need a new space to do my exam, that'll be hard, right? That'll be hard, very hard scheduling wise. We'll try to be, as flexible as we can. The provost, all the way from the president, the provost, the dean, the chair, everybody, is the goal for this quarter is to survive, right? Do as good a job as we all possibly can, be as reasonable as we all can, and survive this thing, and so the thing is, don't cheat on the exams, right? If you cheat and you get caught, it's not good for you. It's not good for this remote exam thing, and that just makes things more complicated. All right, so don't cheat on that, and we'll try to get through this. Any other suggestions? Any suggestions on the things that we should not do, I should not do for the class? Any things you found last quarter that you hated? Okay, all right. Okay, so yeah, so basically, so the structure we outlined in this class is the structure we'll go with. Right, so take a look at the homework. Try to take a look at early. If you need additional time, I know there are people in the class who may have childcare issues, who have caring for other people, need flexing on time. Again, all this can be done. It is much easier if you let me know. Right? You need this kind of flexibility. Right? We'll try to be accommodating. Okay. Right? And I'll try to be accommodating. Right? If you cannot make the office hours, send me an email. One good thing about Zoom is making quick chats much easier. Before it's in-person office, I have to be in the office. You have to come to the office. That's sometimes hard to schedule. Zoom makes that actually quite a bit easier, right? So do take advantage of that. Okay. So if there's no issues, we'll start with transformers today. Right? So this is a technical part of the class. So the slide is also posted, and we'll look at transformers.
Professor, I had one quick question before
we
move
go ahead.
on. Okay, maybe it's more of a comment, but I was gonna ask if you said something about maybe correlating the text to material that we would be covering. Are you gonna be doing that a little bit ahead so that we could?
Yeah. Oh, yes. Yeah. So after this lecture, I'll go to the class website. I'll mark the sections. All those topics will be from.
Okay.
Right,
awesome.
so you'll see that clearly. Yeah. I'll go back and mark it. Yeah. Yeah, so if you don't have the textbook, the slides should be self-contained. But the good thing about the textbook is there's more exercise in the text, more examples on the textbook. Right, so some of the homework comes from the textbook, but all the homeworks will be typed out. So you don't need it. If you really cannot get access to it, you don't need it. But now I've seen enough copies out there to know. You should be able to get one if you really want to. Okay, there's more than enough copies of this textbook floating around out there. Yeah, I will go to the class website and mark these sections. These things are coming from. Okay. And the thing about the class is basically I will write on the slide and they will be posted after. So if you look at the slides, you'll see some blank spaces. Those are by design. Okay, so that you can follow along when I write stuff, right, during class. Okay, so don't be alarmed. You see big blank spaces in the slide. Those are intentionally left blank. Okay. But transformers and power system, basically, we have all seen this power system. The power system looks something like this. I have a generator. I have the transformer. I have a transmission line. I have a load. Okay. And when you look at large power systems, our goal is to make sure, right? So to write this whole thing as a circuit, meaning I have a voltage source, some resistance, some, some kind of this circuit, right? So this is our goal. We're going to translate this to a circuit. It turns out transformers is one of the more complicated things to translate into a circuit like this. Okay, because we'll have a transformer every time we change the voltage setting. So this is the up conversion transformer. For example, this may go from 10 kV to 100 kV. This go from 100 kV to something like 20 kV, so industrial load. Okay, so transformers are tricky to get correct in a circuit model. Okay? And our goal is to understand how do we do that. So the first two topics in the class is actually, one, understand the model of transformers. Two, how do we get rid of it in the circuit? Basically, how do I not deal with the fact that I'm doing voltage conversion in the power systems? Okay, and that, though it's maybe simple, but it's actually a big reason why we can use sophisticated softwares. Is because I can abstract away the transformers. Okay, so our goal in the first two classes is to do this. Okay. So before abstracting away the transformers, right, we need to understand the model. Right? So again, transformers are used all through the system. As we have a lot of generation shifting in the system. We have, generation tends to go from 11 to 30 kV. There are many different level of transmission lines. Residential is 240, 120. Okay. So the reason we have an AC power system is actually comes from the fact that we can build a transformer. It's easy to build AC transformers. So that's why we have an AC system. Right? We have many different levels. And so how does transformer work? Well, so we have all seen this diagram. Transformer is basically something that's wrapped in two coils, right? So we have a core in the middle, and we wrap coils around it. Okay, so what do we do around these two coils? We set up a voltage along one side. We flow a current into this transformer. So what happens when I flow a current into the transformer? What happens in the core of the transformer? The review from 351. What happens once the current starts flowing from, let's say, the primary side of the transformer? I have induction. Basically, I set up magnetic field, right? I have a magnetic field now inside the core of the transformer. And because this is an AC current, right? So it's a time-varying magnetic field. And the time-varying magnetic field now induces a time-varying electric field on the wires. And hence, I have current flow out of this way. Okay, so this is my transformer. And I have a field flowing. So this H is the intensity field, and this is a magnetic intensity field. And I set that up, and I have some flow. Okay, so, and how much this flow is controlled by three parameters. So in 351, we did not go into a lot of detail about transformers. Here we'll go a little bit more into detail. We'll try to get a little bit more into detail, try to understand why it works. And if you buy a transformer, right? Again, you stay out of state light. Why do you spend $50 million building a transformer? And believe it or not, I got newspaper people calling me and asking me why it costs so much money for us to build a new transformer station, right? So that's something good to know. Right? If you work for City Light and you got cornered by a camera and ask you why does it take so much money, these are some parameters that matters for transformer design. Okay? So one thing that matters is core permeability. Mu C, right? This basically controls how conductive this is, right? How much field this thing can carry. And this is a measure of how much it is close to a perfect conductor. A perfect conductor has something that's infinity. Copper has something that's very high, right? So this is one parameter that controls how good my transformer is. Another thing that controls how good my transformer is something called a core cross-sectional area. AC. Okay, basically says how big this core is, right? Is it a very small core or is it a big transformer? Right? All of these matters, how much it flows. And I have another thing here that's has to do with the length of the magnetic circuit, LC. Okay? What this does is says, since this is a closed metal, think of this as a closed metal body, let's assume the field all flows within this. Then how long does it take for this length to circle back to itself? Basically, this controls, so the cross-sectional area controls how the wide it is, and the circuit length controls sort of how, together they control how big it is. Okay, and how the transformer works depend on the size and depend on the materials made of, which is controlled by mu C. Okay, so these are the core parameters in the transformer. Any questions? Right, so look at some equations to try relating all this so-called parameters, the transformer parameters, to things like the magnetic field, to things like the voltage, trying to understand how they impact the transformer. Okay. All right, so I have a transformer and all the things around it. So what equation can we use, right? So this H basically has a unit of amperes per meter squared, right? This tells us this is the intensity field and has the idea amps per meter. This tells me if I go along a little bit distance, how much more magnetic field do I pick up? Okay, so this is the interpretation of the H number. And the law that controls this is the following, right? So if you do a closed path integral of the H field we have in this core along this closed path, right? So if you integrate this thing along the closed path, this is the total current we have that's enclosed. Okay, so if this is a shock to you, you've forgotten all but path integrals, this just means that the net amount of magnetic field is equal to the current, or the net current flow, right? So if I trace along the core, at each point I measure how much current is flowing per meter. Then if I trace around the closed path in the core, this is my net current I have in the core. Okay, I have this net current. Okay, so why does the net current matter? Why do I care about the net current? Well, we're going to assume HC is a constant. Okay. And we're going to assume that the intensity doesn't vary very much in the field. And what this allows us to do is to relate HC to the current. Because on one side, the path integral becomes HCLC, right? I'm integrating a constant along a path of length LC. So this is HCLC, a constant number. Okay? And this equals to the current that I'm enclosing in this transformer. Okay? So how much current do I have in this transformer? If I look at this path, okay, so let's look at this path. How much current am I encountering? If I look at the current flow along this winding, how much net current is here? If I look at this, so I have I1 flowing and have this N1 number of coils. How much current do I flow? Right, this is N1 coils or N1 windings. And each of them, I'm flowing I1, right? So here gives me a net input of N1 I1, right? Because I'm looking through this field, I'm counting the current I have. This current is being injected on the primary side by let's say a constant current going through N1 windings. So this is N1 I1, okay? Now let's look at this side and say I have N2 coils, okay? Here the current is flowing out, right? It's flowing outside. So it's a minus sign. And so for net current, how much net current is flowing out? Here. Right? Okay, so right. So flowing in is I1 times N1. Flowing out, how much is this? Let's try this interaction thing. And yes, so this is N2 I2, right? So the current balance, this is our current balance. Primary side N1 I1 in, secondary side N1 I1 out. Okay. So we're getting closer to the transformer equation now, right? Okay, so this is Ampere's law, basically, right? This is Ampere's law. Net current equals to net injection minus net outflow. Okay, so that's not bad. That's a simple equation. And our goal is basically try to make this zero, right? Because if you remember the standard transformer equation, so from 351, what we have is N1 I1 equals to N2 I2, right? Now from Ampere's law, we have HCLC, which is current enclosed, net current enclosed, as N1 I1 minus N2 I2. So our goal is we need to get rid of this left-hand side. And let's see if we can get rid of this left-hand side and recover the equation we have from 351. Okay, right? So the next is a detour through the field equations, try to get rid of this side. So how do I get rid of this side? Now we need to look at something called a flux, okay, called a flux. So basically, B is a magnetic flux. Magnetic flux inside the coils. Magnetic flux is mu C times Hc, right? It's a core permeability multiplied by the intensity of the current. So this has a unit of Weber per meter squared. Basically, if I look at a cross-sectional area, how much magnetic flux am I seeing? Okay, how much thing am I seeing? And then we're going to multiply this by the cross-sectional area, phi c, to get a absolute number to go away from a per unit. Sorry, to go away from a per meter squared. We're going to just look at the Weber. That's how much field, the net field I have in the flux. Okay, and the goal is to relate this numbers to the Ampere's law we had before. Okay, we're going to try to relate this to the Ampere's law. Okay, so let's try to do this. Okay, so these are the three equations I have, right? HCLC is equal to N1 I1 minus N2 I2. This comes from Ampere's law. The other two come from the flux equations. Okay, and now let's try to put all of them together. Okay, let's try to put all of them together. So if you want to look at this, what we have is, let's look at, let's look at the, right, okay, so let's look at this equation. All right, so let's try to relate them together to each other. So first of all, let's look at this equation that's HC mu C equals to BC, right? This way I can write this as HC equals to BC over mu C, okay? Right, so it's HC equal to BC over mu C. And then I can, from this equation, I have BC is equal to phi C over AC, okay? Substitute here, I have phi C over AC times mu C. Okay, so that's the equation. From getting all these equations, we have the following term. Okay. And then what we have is N1 I1 minus N2 I2 equals to LCHC. Substitute HC from above. Okay, we're going to do the substitution. So what we have is this equals to phi C over AC times mu C. Okay, we have this equation. And then our goal is to, so we're going to pull these things together. We're going to have something that's following LC, mu C AC times phi C. Okay, so this is the net current we have. Okay, this is net current we have. And let's look at what this means, right? What this means is the following. We basically have a magnetic force on the right-hand side, okay? And what we can define is, we'll define this RC as a coefficient, okay? So remember LC, mu C, and AC, these are the three coefficients, these are the three parameters defined by how we make the transformer, right? There's the permeability of transformer, which is the material. There is the LC, how large it is, AC, how large it is. So all this combined, we can combine them into a number. This is called a core reluctance. And what reluctance means is I'm a conductor, right? You're trying to flow current in me. So I try to oppose this current flow. Okay, so I don't like a current being flowed. I'm trying to create a field that opposes the current flow. Okay, so this is called, we have N1 I1 minus N2 I2 equals to RC phi C. Okay, so this is our equation. The net current I have in the system depends on this parameter called RC, which depends on how I make the transformer. Okay, this depends on how I make it. And then we're ready to recover the 351 equation. Okay, we're ready to recover 351 equation. Because what is the ideal transformer? Okay, so again, let's look at this. Mu C AC. So for ideal transformer, what is the value of mu? Right, so for ideal transformer, LC is something, right? How AC is something, just how big the transformer is. So the changes from an ideal transformer to a non-ideal transformer must be in the term of mu C, the permeability of it. So what do you think the mu C is for ideal transformer? Infinity, right? Ideal transformer means I have a perfect conductor, that's a core. So my core can allow current flow or field flow with no resistance, with no reluctance to it at all. So in an ideal transformer, mu C is infinity. I have infinity being mu C. That's infinitely permeable, but it doesn't oppose flow at all. So I recover the 351 equation, N1 I1 equals to N2 I2. Okay, so that's where we get the equation from, right? For an ideal transformer, The net current inside of it is 0 because all the current I put in comes out. And the reason that is I don't lose anything in the core. The core lets everything flow. Okay, and so that I require my ideal transformer. All right, so and for this, any questions about this ideal transformer calculation? Basically, in this later, probably next lecture, we'll do is we'll see what happens when mu is not infinity. Right? So for most conductors, mu is not going to be infinity. Right? So that's a non-ideal transformer. We'll try to relate the non-ideality, meaning mu is a finite number, to a circuit model. But for now, this is the derivation to get the ideal transformer equation. Okay. Any questions about this? Yeah, go ahead.
Are your annotated slides going to be on your page, because you have the unannotated ones?
Right. Yes, they'll be posted after class.
Okay, thank you.
Yeah, so right after this class, I'll post the recording and the annotation. Yes.
Okay, thanks.
No. Yeah, so annotation will be posted. And if you cannot read it, let me know. Okay, because when you do your exam, you're probably looking at the slides. Okay, then the worst thing for you is, I can't read your writing on the slide. I've had this happen to me. And in the, on the exam, somebody will say, oh, on your slide, slide 5, I can't read it. Can you tell me what it is? By that time, I have forgotten what I wrote on the slide. Okay, so you cannot read it. Let me know. I'll try to write better. I'll try to typing it up or something. But I prefer not to type it up. I prefer to write as we go along. Okay? So the last thing in this class is we'll look at this, how we draw ideal transformer. Okay, this is a symbol we'll have for ideal transformer, right? So you have all seen the symbols in your circuits. There's 2 dots with 2 bars, and what we need is in this thing is we need to basically define the polarity. Polarity meaning is the current flow in and out, in or out, and which way is the voltage measured from. Okay, and this is a convention, but it's very important to denote this in your transformer, right? So in this case, I1 is flowing in, I2 is coming out. Okay, and this is the convention. We need to define when we draw a transformer. And the voltage is measured from, the voltage is measured according to the direction of E1 and E2. Okay. So a question for you guys, does the direction of the transformer matter? We have a transformer. Is it a natural way to tell primary from secondary? No, right? The transformer just have 2 coils around it. And you can define whichever way is primary, which way is secondary. How you want. It's not directional, it's bidirectional. But when we draw in a symbol, we need to say which one is primary, which one is secondary. Because by convention in the circuit, we need this. Okay, so you need to mark this. For example, you have a homework question saying draw a transformer, ideal transformer, you need to mark it. Which one is 1, which one is 2, which one is current in, which one is current out. Okay, just say notation-wise. We need to know this when we do analysis, but when you buy an actual piece of transformer, it is completely symmetrical. Okay, there's no way to tell which one is which. Okay, there's no preferred direction in your transformer one way or the other. Okay, we just need to mark this. Okay, so today we'll end the lecture here. Next class we'll go much deeper into transformers. We'll look at voltage, we'll look at non-ideal transformer, we'll look at circuit model and so on. Okay, so today we'll end here. So if you don't have questions, see you next Monday. You have some questions you want to ask, you can stay after class. I'll stay here. Okay. But I'll end the recording and see most of you next Monday.